Now, again, we have the equation y prime equals p of t y, and suppose psi is a fundamental matrix for this equation. Then, of course, psi prime equals p of t psi. Okay, now let y prime equal p of t y plus g of t be a non-homogeneous system. Okay, then we want to find, and let psi be the fundamental matrix for the homogeneous system. This is a homogeneous system, so that's this psi. We want to find a solution to the non-homogeneous solution, and we want to find a matrix solution. It turns out that that's actually easier than going to separate equations and finding a solution. So what we're going to assume is that there is a solution to the non-homogeneous equation that's of the form psi of t times u of t, where u of t is a vector function that we have yet to discover. And we want to try to discover this function, because if we do, then we'll have a solution to the whole system, okay, which will just be psi of t, the solution to the homogeneous system, plus this solution, which gives us our non-homogeneous, it gives us our g of t. Okay, well, okay, if we have a solution to the non-homogeneous equation, then we plug this into our non-homogeneous equation, see what we get. So we get the derivative of this solution, the derivative of our psi of t u of t solution, our proposed psi of t u of t solution. It's not a solution yet. And that's going to equal p of t times that same solution plus our g of t. Well, we take the derivative. That's just done using the product rule. And of course, we've been over the work on matrix multiplication and calculus of matrices and so forth. So we should understand, and we should be able to prove, that the derivative of the product of these matrices is a product. We can apply the product rule to get the derivative of this product. Now, I understand not everybody has done that, so you're going to have to accept it, but it's true. Things work out just about the way you would expect them to, analogous to what we get in calculus. Again, I do urge you to understand why, so that you can check yourself if you ever need to make an assumption that you're not sure of. And you should always be unsure of your assumptions unless you can prove them, ideally. Okay, so anyhow, this derivative is then psi prime of t times u of t plus psi of t times u prime of t. That's equal to the right-hand side. Now, how can we use the fact that psi prime of t equals p of t times psi of t to simplify this? Well, there are two ways to look at it, and actually the way I approached it in the document is perfectly easy to understand, I think, but equally easy to understand is we have psi prime of t down here, don't we? If we just substitute p of t psi for psi prime of t, which we can certainly do, this is what we get for this term. And then, lo and behold, this term matches this term. So we subtract this from both sides, both this term and this term disappear, leaving us our psi of t times u prime of t equals g of t. And that's a relatively simple equation, easy enough to solve for u prime of t. Now, when we did variation of parameters originally, remember that we got a formula for our u prime of t function. You know, the u1 prime, u2 prime equals, etc. So, when we do this, we're again going to get a formula for our u prime. And of course, this is a vector. And this incidentally applies not just to 2x2 systems, but by n systems, 12x12 system, 38x38 system. U is going to be a column that has that many functions, Okay, it's going to be a column of, if it's a 12 by 12 system, it's going to have 12 functions, okay? So anyhow, this applies no matter how many, so this is really pretty neat. Okay, so how do we solve this equation for u prime of t? As before, if you've got u prime of t, and if you can integrate those, the functions that make up your u prime, then you have your u vector, which you can multiply by your psi matrix and get your particular solution, okay? So, well, to solve this equation, we just multiply both sides on the left by psi inverse of t. And now why can we do that? We've got to be able to invert psi in order to do this, but psi is fundamental matrix of a fundamental set, and its Wronskian has to be non-zero in order for that to be the case. Well, the Wronskian's just the determinant, so that the psi matrix is automatically invertible. If you've checked the determinant to make sure you really have a valid psi matrix, it's going to be invertible. So we do this, and we end up with u prime of t just equal to psi inverse times your g vector. Very similar to what we got when we did the variation of parameters with second order linear equations. Okay, well, it's going to work out that way, so that u prime is psi inverse times your g. Then, to get u, we're going to integrate. Now, I'm going to step away from the board just long enough to see how long this video is running. Yeah, we're within tolerable limits. We're doing okay. So, to get u of t, then, we have to integrate this. And when we integrate this, we're going to get an integration constant. Well, I'm just going to put the integration constant out here. Kind of automatically comes, and then times any antiderivative of this. We don't have to include an integration constant in this antiderivative because we've got it here. So what's our solution? Okay, the solution we get then is psi of t times u of t, where u of t is this. So psi of t times u of t is, well, psi of t times u naught plus psi of t times this integral. Okay. The psi of t times u naught is just a constant column vector. It's a vector consisting of just a bunch of numbers. So if we do psi of t times u naught, our columns are just going to be linear combinations of our original psi of t vectors. So that this vector is going to be going to represent some linear combination of our fundamental set of solutions to the homogeneous equation. Meaning that this is a perfectly valid characteristic solution. It might not be a general characteristic solution, but it is going to be a linear combination of our solution vectors. And it's going to be a solution to our homogeneous equation. If we can do the integral of psi inverse times g of t, in other words, if we can integrate every one of the n functions we'll have for an n by n system that make up the psi inverse g of t column. Remember, g of t is a column of n functions. And it's actually, to indicate that, I should have an arrow. Oh, I'll find a good piece of chalk, I'll put an arrow over it. Not a great piece of chalk, but it'll do. Okay? Should have had that arrow there in the first place. Okay, so remember, this is, if for an n by n system, a system of n simultaneous differential equations in n unknowns, y1, y2, up through yn, the psi column will be, the psi matrix will consist of n columns, each of vectors n units, n entries long, of length n. So each column will be length n, there will be n of them. You'll have an n by n matrix. G of t, in order to be compatible up here, has to be a column of n functions. If I multiply an n by n matrix by a column of n functions, I get n functions. I have to be able to integrate all of them. And I'll get a column of n functions and antiderivative functions, which I then multiply by my psi of t matrix, giving me a different column of n functions. That will be my particular solution. Now, you might want to come back to that whole thing about n vectors and n functions after you've worked a couple of these, if you don't completely understand what I'm talking about now, but that's what's coming up. Okay. Then I have the comment here that I've already made. For a general vector, u naught, which is a constant vector, I should say a general constant u naught. I said up here it's constant, but I didn't say it down here. A general constant u naught, the psi of t will still be a solution to our homogeneous equation. And there are many ways to prove that. It's just basically write it out in a general form, and it's easy to justify every step. That is then, if u naught is c1 through cn, and psi of t consists of column vectors y1 through yn, then psi of t times u naught is just c1, y1, c2, y2 up through cn, yn. Just a set of multiples of our y1 through yn. And if none of these c's is 0, we're going to get then linearly n linearly independent column vectors, and all of those vectors together would make up a fundamental set. So if we did the set consisting of c1, y1, c1, y2 through c1, yn, it would be a fundamental set for our system of differential equations. And in any case, this matrix is still a solution to our homogeneous equation. It's still a characteristic solution. And if none of the c's is 0, none of the c1 through cn's is 0, not only is it a characteristic solution, but it's a general characteristic solution. And I'm actually not sure that I want to make a distinction between a characteristic solution and a general characteristic solution. None of the c's is 0, it's a characteristic solution. How about that? Okay, well, that's everything and probably more than you need to know.